Today we're going to take a look at the changes in potential and kinetic energy of a pendulum. This is a pendulum, simply a mass suspended from a spring, and the length of the pendulum is always determined from the pivot point where the pendulum is connected to the center of the mass of the pendulum. Center of mass, not to the top or the bottom, but the center of mass of the pendulum. That is the length of the pendulum. So what we're going to do, we're going to move this pendulum some angle, this direction, and I'll let go of it. It's going to oscillate back and forth. Notice the larger the angle I pull it, the faster it's going to be moving at the bottom of the path. Now, what we want to do is analyze the energy relationships between the angle at which we move this and how fast it's moving at the bottom of the path. The thing to remember is, this at the bottom of the path, like it's located at this point right here. I know that's hard to see with this pen at this point. But if I move it to an angle, I'm actually lifting up some vertical height. There's some vertical height that this pendulum bob has been lifted. So at this point right here, at its highest point, it's not moving. So it has some potential energy relative to where it started at the bottom. As I let go of it, this potential energy is as if the object is falling in free fall, except it's moving in an arc. But all this potential energy here is going to be converted to kinetic energy at the bottom of the path. Now remember, we said that we can determine the zero potential energy level at any position we want to. Well, let's say the bottom of the path is a zero potential energy level. So at the bottom of the path, it has no potential energy, but it's moving. You can see it's moving when it's at the bottom of the path. So it only has kinetic energy at the bottom of the path. So what's happening is this potential energy is being converted to kinetic energy, just like as if we had an object and we dropped it straight down. An object has potential energy at the top and kinetic energy at the bottom. So we're going to analyze these energy relationships, see if we can determine different characteristic things about this pendulum as we go through these different types of problems. We have two different problems you can do with pendulums. We're going to do a couple of them and use energy relationships to analyze it. Sorry for the camera motion here, but I'm going to go to our notes then. And you need to either have a blank notability page or have a piece of white paper. Sorry for the camera movement, but I gotta get set up here. Either have a piece of white paper, I'm going to use white paper, or you can use a blank page of notability. Let's see how we can do some of these problems. So let's take a look. So this is the conservation of energy in a pendulum. So we're going to draw a diagram of a pendulum, see if we can analyze that information. So we have a pendulum. Be suspended from some rigid point. And make sure you draw a long enough pendulum. Don't make it too small, because we're drawing a lot of different things on here. And let's say for right now, we're going to move this pendulum to an angle to the right. Doesn't matter if we move it to the right or to the left. And we're going to move this to an angle of about 25.0 degrees. You can measure that with a protractor if you want to. Again, this isn't to scale. We're going to say the length of the pendulum. Remember, the length is from the center to the pivot point. So this length of the pendulum, we're going to say to be 0.750 meters. Okay? Now the length of this pendulum doesn't change. When I pull this pendulum up to the side, the length of the pendulum doesn't change. So from the center of this mass to the pivot point, this is still the length of the pendulum. The pendulum is still 0.750 meters. So the length doesn't change just because we move it through some arc. Now what has happened is, if we extend the center of this pendulum out this way, and take the center of the pendulum at this point right here and extend it horizontally this way until it reaches the vertical position of the pendulum, what has actually happened is we have raised this pendulum some height h. All right? We don't know what that is yet, but we're going to figure that out here in just a little bit. What we want to do, now it's velocity right here at the highest point. Its velocity at the top, v sub t is top, is going to be 0 meters per second because it's not moving. It goes to its highest point and it stops there. Just like we throw a ball straight up in the air. And we want to determine what this final velocity is of the pendulum at the bottom of the path. Okay? Well, let's see how we can do that. Remember, we're going to use energy relationships to do this. Remember, when you use energy relationships, it can make what might seem like a complex problem actually become a fairly easy problem. So let's see if we can do this. At this point right here, law of conservation of energy says that all the energy that it has here must be the same as all the energy that it has there. So at the beginning of the path at the top, what type of energy does it have? It has potential energy because it's not moving and it's some distance above. We're going to say the lowest point of the pendulum. We're going to define that as 0 joules of potential energy. So this is our 0 joules of potential energy level. So at the top of the path, we'll put P sub T for top. That's a T. The potential energy at the top, it only has potential energy at the top. Then at the very bottom, the only energy it has at the bottom is kinetic because it's moving at the bottom of this path. And so we'll say the kinetic energy at the bottom. All right. Now, let's put these variables in for here. This is going to be mgh, the height at the top of the path. It's going to be equal to 1/2 mvb, velocity at the bottom, squared. All right. So let's take a look. I didn't give you the mass of the pendulum because, look, we don't need it because this mass cancels out. We know what g is. We're solving for v, so the only thing we need now is this height. This height here, how do we get that height? That's the kind of a new thing in the pendulum problem. This is the same we've been using for the past several days. Total energy to start equals total energy at the bottom. Law of conservation of energy. But how do we get this height? Well, let's take a look. This height here, again, this is the height. This height and this height are the same thing. This entire length from this point to this point is 0.750 meters. Well, I'm going to call this section from the top to here, from there to there, is going to be, from there to there is, I'm going to call this y. Because this is a right triangle. This is a right angle right here. This is a right triangle. We know the hypotenuse of that right triangle is 0.750 meters. We know the angle. So let's figure out this side right here. From that point to that point, we can figure out this y. So this is the adjacent side of this angle, so we're going to use cosine of 25.0 degrees is equal to the adjacent side, we're going to call that y, over 0.750 meters. Now you should be able to do the math on this. This y is going to be 0.68. Let me make sure I do that math correctly. I want to clear everything. This is going to be 0.750 times cosine of 25.0 in parentheses. It's going to be 0.6797. So when we say round it to 3 significant digits, 0.680 meters for this y distance. But remember, we want this h. Well, this is y. This is this part of the length of the pendulum. We want this part of the length of the pendulum. So if we take the entire length of the pendulum from this point to this point, which is 0.750 meters minus 0.680 meters, that is equal to the height of that this pendulum fell from this point to this point. And that height is going to be 0.070 meters for that height. Right? So now we can put that in this equation. So I'm going to put it at 9.80 meters per second squared times the height of 0.070 meters equals 1/2. So I'm kind of squeezing this into velocity of b squared. Separate that. We solve for this velocity of b. You do the math on that. You can pause this video. You can solve for that velocity right there. You can take 9.8 times 0.07, multiply by 2, and then take the square root of that number, and we should get 1.17 meters per second for the velocity of b at that point right there. All right. Let's see if you can duplicate that. What I'd like for you to do, I'm going to write this problem out. It's very similar to this, and see if you can solve this problem. Very similar to what we're going to do. We just put some different numbers in, slightly different direction. We're going to move the pendulum to some angle. Let's see what you can do. So this is what we have. We have a pendulum, and we initially have it suspended down. And we say the length of this pendulum from here to here, this length, is going to be 0.450 meters. We're going to pull it to the left. It doesn't matter if you go to the left or right. The analysis is really the same. We're going to pull it to the left, and we're going to pull it at an angle of 35.0 degrees, 35.0 degrees. And what we want to know is what the final velocity is. I'm going to put v sub b for the bottom. You can put vf if you want to. This is the final velocity at the bottom. When we let this go from here to here, how fast is it going to be moving at the bottom of its path? I'd like for you to pause the video and see if you can solve this problem. And once you have it solved, start the video back up, and I'm going to go through the solution for you. Now, you need to know how to do this. Just don't keep the video going and copy the answer. See if you can do this on your own. You can look at this problem as a reference and see if you can solve this problem, because you can have a quiz tomorrow over motions of a pendulum using conservation of energy. So pause the video, see if you can solve the problem. All right, hopefully you paused the video long enough and solved the problem. Let's see how we did. So this is what we have. This pendulum length is 0.450 meters, which means this length from here to here is still 0.450 meters. All right, that length is 0.450 meters. We draw a horizontal line from the center of this mass and a horizontal line out from the center of this mass. This is the height which is the same as this height. This distance and this distance is the same. So what I'm going to do, I'm going to solve for, in order to get this height, we need that height right there because that's the height that it fell. Remember, the bottom of the pendulum we're defining as 0 joules of potential energy. We have to define 0 potential energy level someplace. We're going to define it at the bottom path of the pendulum. So we wanted to get this height in order to solve this problem. So we first had to get y. So this is the adjacent side. Remember, this is the right triangle. So I'm going to do cosine at 35.0 degrees is equal to the adjacent side y over 0.450 meters. We get that y to be 0.369 meters. But we want h. So in order to get h, we have to take the entire length, 0.450 meters, minus 0.369 meters. We get the entire height to be 0.081 meters. That's the height that we have to use. Now we can use our conservation of energy. The total energy it has here, which is potential energy, because it's not moving, it only has potential energy, equals the total energy it has here, which is only kinetic energy, because it's at our 0 potential energy level. So we have the potential energy at the top, piece of T is top, must equal the kinetic energy at the bottom. We're solving for this final velocity. So we put in mgh at the top equals 1/2 mvb, velocity at the bottom, squared. Don't forget to square that. The masses cancel. I didn't even give you the mass of the pendulum, so we hope it cancels, and it does mathematically. It's going to be 9.80 meters per second squared times the height, which is 0.081 meters, equals 1/2 times the velocity at the bottom squared. If you do that calculation, the velocity at the bottom should be 1.26 meters per second. So that's one type of problem. And both of these, the demonstration problem and the practical problem they did, we're solving for the velocity at the bottom of the pendulum. Now we're going to go a little different way, give you some other information, and but it's still, the problem is still going to be solved using conservation of energy. So now this is what we have. We have a pendulum, and we have it pulled back. Let's do this. We have it pulled back. This is the pendulum. We have it pulled back at some angle to the vertical. This is as if the pendulum were suspended straight down. The pendulum is going to start here and fall down. It's going to reach this position right here. And we know the angle of this pendulum. This angle is going to be, I'm sorry, we don't know the angle. This is what we're trying to find. We want to know this angle of that pendulum. There we go. So we measure the velocity this pendulum has at the bottom of the path. The velocity at the bottom is going to be 1.50 meters per second. And we want to know what this angle is. The length of the pendulum, the length from the center of the pendulum to the pivot point, this length is going to be 1.25 meters. This pendulum is going to fall, reaches this bottom point, falls, reaches this bottom point, it's going to be moving at 1.50 meters per second. We want to know what the angle of that pendulum was when it went from here to the bottom. At the bottom is moving at 1.50 meters per second. Well, this is what we have. We know that the bottom of the path has kinetic energy. We're going to say the bottom of the path, again, we take this horizontal line from the center of the bottom of the location of the pendulum. We're going to call this our 0 joules of potential energy. And we take another line from the center of the pendulum to the vertical position of the pendulum. And this right here is going to be the height that the pendulum actually fell. This distance here, from this point to this point, this is y, just like we've done before. But now what we have, we know the velocity at the bottom of this path. So what we're going to do, we're going to start here. We're going to say all this energy here has to equal all the energy at the top. We'll say this pendulum is oscillating back and forth, and it's going to be moving this way. Here it's moving at 1.50 meters per second. It goes up to reach this, it goes this way. It's oscillating back and forth. Reaches this point right here, moving at 1.50 meters per second. All the kinetic energy at the bottom is going to be converted to potential energy when it reaches the top of its path. So we're going to do it this way. We're going to say all the kinetic energy at the bottom, we're going to start here and end there. So the kinetic energy at the bottom equals the potential energy at the top. Now you can do it the other way. You can say the potential energy at the top equals kinetic energy at the bottom. It amounts to the same thing. Put these variables in. This will be 1/2 mass times the velocity at the bottom squared equals mgh at the top. Again, the masses cancel. They're on both sides of the equation. We know this velocity, we know g, but we need to solve for this height in order to eventually get this y and that component. So we're going to solve for h using this. And so we're going to put in 1/2, the velocity is 1.50 meters per second all squared equals 9.80 meters per second squared times this height, which is the height it went vertically from the bottom to the top. Do the algebra on this, and this height is going to be 0.115 meters. Keep correct significant digits. Now, in order to solve for this angle, remember this is the adjacent side, and this is the hypotenuse. In order to get this angle, we need two sides. Well, we have the hypotenuse, 1.25 meters, but now we need to get this y. We know this h, and again, this total length from there to the bottom, the entire length from there to there is 1.25 meters. So if I subtract this height that I have here from 1.25 meters, we get y. So y is going to be equal to 1.25 meters minus 0.115 meters. And if we get that calculation, we will get 1.135 meters. Now we know this y, and now we also know, and we know the length, so now we can get that angle using cosine. So we now have cosine of theta is equal to the adjacent side, which is 1.135 meters. Now if you want to convert that to 1.14, you can. It won't make a whole lot of difference, maybe a little in the angle, but not much, over the hypotenuse, which is 1.25 meters. We solve this angle. Again, you should do the algebra to see if you can solve for this correctly. We get that angle to be about 24.7 degrees. Right? Notice we still use, no matter whether we're solving for the angle, we're solving for this height, we still use total energy at one point must equal total energy at the other point. This way we start at the bottom, use kinetic energy at the bottom equals potential energy at the top. We could have switched those around, math would have worked out just the same. So now what I want you to do, I'm going to give you another problem similar to this one up here. I want to see if you can solve it on your own. All right, let me give you the information here. And so we're going to have a pendulum, and it's going to be pulled this direction, and it's going to fall down until it reaches a vertical height. We'll say, try and draw this a little better, to that position right there. And we don't know what this angle is. We're going to solve for this angle that we pulled it back, and we measure this velocity at the bottom to be 1.75 meters per second. The length of this pendulum from the center to the pivot point, that length, is going to be 1.50 meters. 1.50 meters. So that's the information you have. We want to ultimately solve for that angle right there. Again, pause the video. See if you can solve this. Very similar to what was done in this example problem. So do this practice problem, pause the video, see if you can solve for that angle. Use this information we did up here as your guide if you need to. Pause the video, solve the problem, then come back and we'll take a look at the solution. All right, hopefully you paused the video and went through the solution with this. Let's see what we can do. Again, we're going to start at the bottom here. We'll assume that this pendulum, it oscillates back and forth like this. We'll say the pendulum's coming this way. We're going to start at the bottom here. It's moving this way. At the bottom, we know it has some kinetic energy because it has a mass and a velocity. So we're going to say the kinetic energy at the bottom is going to equal to all that kinetic energy is going to be converted to potential energy at the top. Potential energy at the top. Now, when we do this, we draw a horizontal line from the center of the pendulum at the bottom, horizontal line towards the direction of it was moved, and we draw a horizontal line from the center of the pendulum at the top of the path to the vertical position. This right here is the height, and we have to get that height in order to solve ultimately for this angle. Now again, this distance right here from there to there, we're going to call y. Okay? This entire length from there to there is still the length of the pendulum, 1.50 meters. And again, this is the height, which is the same as this height here. This is h. All right, so let's put the variables and see what we have. 1/2 mv velocity bottom squared equals mgh, height at the top. Again, the bottom of the path is going to be defined as our zero potential energy level. And so again, the masses cancel, so we have 1/2. The velocity at the bottom, we know 1.75 meters per second, all squared, equals 9.80 meters per second squared, times this height. We need to solve for this height in order to ultimately get that angle. So we solve this for height. You should have this done already. I get a height of 0.156 meters, the 3 significant digits. And now we need to get this y. So we're going to take the entire length of the pendulum 1.50 meters, sorry, this is y equals 1.50 meters minus 0.156 meters, we get that y to be 1.34 meters. Yeah? So now we know this side, again, this is the right triangle, this is the hypotenuse, this is the y, so we know two sides of that right triangle. We can solve for any angle, we can solve for that angle, and we can use cosine. Cosine of the angle theta is equal to the adjacent side, which is y, which is going to be 1.34 meters, over the hypotenuse, which is the length of the pendulum. Again, this is the adjacent side, this is the hypotenuse, 1.50 meters. You should be able to do this calculation, or you should have done already. It should be 26.7 degrees. There we go. All right, make sure you know how to do these problems, understand what we mean by potential energy at one place equals kinetic energy, or potential energy at the top equals kinetic energy at the bottom. And remember, it really doesn't matter. The total energy anywhere along this path, remember the pendulum oscillates back and forth like this, the total energy anywhere along this path must equal to either this total potential energy here or the total kinetic energy here. All this potential energy is converted to kinetic energy at the bottom. Or you can say the kinetic energy at the bottom is converted to potential energy at the top. The energy is always the same as long as there's any energy lost due to friction. Make sure you understand how to do these two types of problems, either solving for the velocity at the bottom where you're given the angle, or solving for the angle where you're given the velocity. All right? You have the quiz tomorrow.